What is the purpose of studying things measured in nature? Mathematics is about observing and understanding nature to uncover the hidden order and rules in nature. Artists depict beautiful nature using colors and shapes, and poets use languages to sing about nature and society. Mathematicians, on the other hand, use numbers and tools like shapes to understand the mystery of nature. It's hard to define beauty in mathematics, but it's not very different from beauty in songs or poems. Beauty in mathematics no different from beautiful harmony in music, and pleasant rhythms in poems. Mathematics is a study to develop a predictive model by uncovering the causation of phenomenon in nature or society through a series of observation. The mathematical way of arriving at a conclusion is to come up with the best solution for any given conditions. People are always forced to make choices. Here, information is critical to make the right choice, and biased information is not useful. Comprehensive thinking is needed to process information effectively. Life is about series of making choices and facing consequences. People have to select one option out of many or forced to choose an opinion. In such situations, it is important to make the right decision by selecting the best option. Here, mathematics can be the basis of the accuracy and rationale behind a person's thinking process. Mathematics helps to build logical and rational thinking process. However, in reality, most mathematics today is strictly limited to calculations, causing a lot of students to lose interest and motivation to study. For most students, the first impression of mathematics is that the subject is about solving problems. They are also forced to come up with answers before understanding any logic or conditions behind the problem. That's why most students equate mathematics with problem solving. Students who focus on finding answers instead of finding the meaning behind these math problems are not interested in logical reasoning behind mathematical theories as well as the application of mathematics in real life. Unfortunately, these students do not have the capacity to understand the value that mathematics hold, a subject that is closely related to humanity's happiness as it holds the secret to longevity. Although people try to make the best choice in any given situations, they do not realize the important role of mathematics during this process. The impact of mathematics may vary from a person to another, but it's evident that it has a significant impact in people's everyday lives. You may not be able to grasp it to the fullest extent, but mathematics is a necessity for humanity's survival. It is also a subject that can maximize the capacity of humans. Without proper mathematics, countries or companies may lose its competitive edge for survival. The world of mathematics is full of pictures known as figures. From stars in space to small plates around us, figures are everywhere. Mathematics play a significant role throughout the process of discovering and understanding these figures. That's why we study measurements as part of mathematics. Measurement is not just tools to measure objects. Each country has its own measurement system that reflects its culture and history. Studying measurements can help to understand the political and economic characteristics of a country. It's a well-known fact that measurements to measure plane figures are the civilization's bedrock of prosperity. Mathematical formulas that we take and use for granted are the result of years of observing and measuring nature. And during this measurement process, measurement is a system that was developed by the rulers. Humans have drawn changes in nature to find new principles and rules. For example, the concept of time was first developed by depicting the movement of the sun and the moon as circles. Based on this concept, people took a step further to develop more specific ideas such as 60 minutes and 60 seconds. Sexagesimal system is believed to be first used in ancient Babylon. In the West, 1 hour is equal to 60 minutes. On the other hand, most Asian countries do not use the sexagesimal system, except a few East Asian countries. Then why did Babylonians use the sexagesimal system? The only explanation we have so far is that the system may have something to do with constellations. Some say that the system originated from observing a star that has the orbital period of 60 years, but we aren't sure which constellation it was. All ancient civilizations had their unique methods of measuring time. Of course, the history of watches is closely related to this development. The earliest sundials are from ancient Egypt, his obelisks around 1500 BCE. Babylonians based its time on the sexagesimal system, so 1 hour was 60 minutes. Korea had its sundial in the 15th century. By the 17th century, electronic watches were very popular in Europe. Quartz clocks, which use an electronic oscillator that allowed more precise calculation of time, were developed in the 20th century. It's true that there should be only one universal time, but clocks that humans created can never tell the exact time, even though the accuracy has improved significantly. Of course, the difference is so small that it does not have a significant impact on most people's day-to-day lives. But in the face of power, this difference in time becomes a more serious problem. The time difference became a problem during the age of imperialism. Here, the simultaneity refers to a situation when two different incidents occur at the same time. As the country expands geographically, it was essential to know the exact time of a very far distance as it attempts to connect one end to another through its new railroad infrastructures or sea routes. During the age of imperialism, ruling time was fundamental to geographical control and sustaining power. Ancient mathematicians were able to draw the figures without using sophisticated computer programs that can draw them instantly. That's because they understood plane figures well enough to be able to draw any figures using just a rope and a stick. Rhind mathematical papyrus demonstrates how well ancient Egyptians understood plane figures. The book estimates the area of a circle and the volume of pyramids very accurately. The book also contains problems to calculate the area of land in any shapes using the area of a triangle. Measurements help us to understand plane figures, which enables us to uncover the secrets of nature in a more logical, systematic way. How did the rational, logical geometry start in Greece? A book written by Herodotus, an ancient Greek historian, demonstrates an amazing advancement of land surveying techniques in ancient Egypt. His book introduces an interesting anecdote. King Sesostris divided his land into squares and distributed them to all Egyptians randomly and in return collected taxes from their harvest. If the flood destroyed these boundaries, the owner would immediately report to the king. Then, after measuring how much land disappeared, the tax was recalculated to be proportionate to the remaining size of the land. Ancient Egyptians had a remarkable understanding of calculating area or circumference of plane figures such as triangles of squares. If Egyptians were keen on applying calculations to everyday lives, ancient Greeks studied more about the figures. In other words, Greeks were able to develop a more logical and systemic geometry by adding their logical thinking to Egyptians' practical knowledge. It was around this time when most theories on plane figures were developed. Greek mathematics reflects its culture very well. Mathematics at the time frowned upon practical sides of mathematics by Pythagoreans, who succeeded Ionian nature-centered philosophy. Therefore, at the time, mathematics did not focus on calculations, but more on theories of numbers and geometry. When it came to numbers, Pythagoreans focused only on natural numbers or categorizing numbers and proportions. However, their approach hit a wall after they discovered that the length of a diagonal of a square could not be written in a ratio of natural numbers. Nonetheless, geometry in ancient Greece made significant advances. The most excellent example is Euclid's Elements. The book reflects Plato's ideas, where its intricate system and sound logic continued to influence mathematics up to the 19th century. Thales, a Greek naturalist philosopher, contributed to the advancement of mathematics. This in turn laid the foundation for other subjects such as natural science and philosophy. Recent studies on Babylonian mathematics led to the discovery that most knowledge of ancient Greeks was actually from the Orient Empire. The sexagesimal system that Babylonians developed is still used widely today. Babylonians were very active in their research on surveying techniques and calculations. They were very curious about changes in nature, in particular, the sun. They found the sun's movement from east to west very interesting. After years of observation, they discovered that it takes 360 days for the sun to appear at the same location. Interestingly enough, they also discovered that it takes about 360 days for a seed or a tree to sprout again. So, the Babylonians defined a year as 360 days. Their calendar, shaped like a circle after the sun, is divided into exactly 360 parts. This is the birth of the angle. In other words, each degree is a day. The concept of an angle helped us to categorize and study figures easily. However, mathematicians struggle to solve problems about circles that emerge from studying angles. It took them 5,000 years for mathematicians to solve the problem of drawing a square that has the same area of a given circle with just a ruler and compass. For Greeks, the status of mathematics was obvious as a part of science. Compared to ancient Egyptians, Greeks treated mathematics more like an abstract portrait. The knowledge that Greeks gained from the Orient were more practical, such as calculations, geometric measure, and construction of figures. However, the Greeks frowned upon practical techniques like calculations, and believed those belonged to slaves or lower class. As such, Greek natural philosophers and mathematicians heavily focused on abstract problems such as number theories. Mathematics and Greek stem from natural philosophy. The most well-known philosopher is Thales of Ionia, followed by who we know today as Pythagoreans. They advanced number theories further, and studied on the average of numbers, geometry, harmony, and the rules behind proportions. In geometry, Pythagoreans not only came up with the Pythagorean theorem, but also on how to double the area of a cube with an untallied ruler and compass, how to divide an angle into 3 identical angles, or squaring a circle. However, Pythagoreans lost its fame with the discovery of irrational numbers. Irrational number was a wake-up call proof that there are problems that cannot be solved through geometry and theories on similarity. The biggest challenge of studying space is to measure the distance between the stars that are too far for us to travel. Before the advancement in technology, measuring faraway distance was very difficult. However, the discovery of the triangulation method made it possible. Triangulation is the process of determining the location and distance of a point using characteristics of a triangle. You can measure the distance to an endpoint from the angle of known 2 points at either end of a fixed baseline. For example, to calculate the distance to a star, the distance to the star will be the endpoint, and the distance between 2 observers on Earth will be the baseline. Parallax is also used to calculate the distance to stars using triangulation. Parallax refers to a difference in the apparent position of an object when you close one eye. Similarly, the background of a star may be different from a point on Earth, and the difference in sight lines is known as parallax. Using parallax, the distance between Earth and the Moon is about 238,600 miles. As mentioned, the distance to the star can be calculated using parallax. In a triangle with the constant baseline, the angle of the third point will become smaller if the distance is further away. Since the distance between a person's eyes is only 10 centimeters, humans cannot measure faraway objects like stars. That's why it's important to put 2 baseline points as far as possible. One way to do this is to use annual parallax. Because the Earth orbits around the Sun, every 6 months the Earth will be at the opposite end of the orbit. By observing the same star after 6 months and using the information that we already know the distance between the Sun and the Earth, we can calculate the annual parallax. The annual parallax is the half of the actual parallax, or an angle formed by the distance between Earth and the star, and the distance between the Sun and the star. A German astronomer named Bessel was the first person to use the method of parallax to calculate the distance by expressing parallax in terms of angles. We can use a proportional expression to measure the distance between objects using a ruler and a compass. Today, we don't need to use proportion or rulers to measure the distance. Laser machines can do it instantly. Then can we measure something we cannot see at once, like the circumference or the diameter of the Earth? What about the distance to the Moon? We can use a proportional expression to calculate mathematically. With the help of laser machines, it's very easy to measure lengths or sizes. Then what about something that's further away like stars? In fact, it's impossible to use parallax with machines, as all lights from the star to Earth is an almost perfect parallel. Laser machines can't be used because it will take forever to wait for the laser to reach to the star and return. But using revolution or movements of the solar system, we can calculate using triangulation. The most widely used form of triangulation requires parallax. If there is a ruler that can measure anything of any size, we can measure the size of the Earth. All it would need is for a person to walk around the Earth with that ruler. It's like an answer to a question: how do you put an elephant in a refrigerator? The answer is easier said than done. First open the refrigerator, put the elephant inside, then close the door. Measuring the circumference of the Earth may sound easy. However, walking around the Earth may pose a few serious challenges, like climbing high mountains or crossing deep oceans. But with one compass, you can measure the size of the Earth without having to walk around the Earth. Eratosthenes already knew this about 2,000 years ago. Here's how he calculated the circumference and radius of the Earth. He discovered that every noon on the summer solstice in Syene, the sun was directly overhead. He knew this because the shadow standing over a well would disappear and the sunlight would reach the end of the well. Syene, modern-day Aswan in Egypt, was also known as Swenet, which means trade or market, among ancient Egyptians. Located 880 km from Cairo, Egypt and east of Nile River, the city, as its name suggests, was the center of politics, military, and commerce. He then found out that in Alexandria, a city about 5,000 stadia north, the angle of the sunlight from a building is about 7 degrees. Based on such observation, Eratosthenes was able to calculate the circumference and radius of the Earth. 5,000 stadia are approximately 925 kilometers. If the radius of the Earth is r, the circumference of the Earth is 2 pi r, and since the length of an arc is proportionate to the center angle, we can say that a ratio of 2 pi r to 925 kilometers equals 360 degrees to 7 degrees. If pi is assumed to be 3.14, the circumference of the Earth is approximately 47,571 kilometers, and the radius is about 7,575 kilometers. The actual circumference is 40,075 kilometers, and its radius is 6,731 kilometers. Although his calculation is not exact, at the time, this was an accurate calculation. Of course, because a stadium was different for each region, it's impossible to know the exact length. What about the distance to the moon? Ancient people used a proportional expression to calculate the distance. Aristarchus, a philosopher who lived around the same time as Eratosthenes, discovered that it takes about 3.5 hours for the moon to travel through the Earth's shadow. In other words, it means that the moon moved the distance that equals the diameter of the Earth's shadow. If the sunlight shines parallel to the Earth, the diameter of the Earth's shadow is equal to the diameter of the Earth. If the distance between the Earth and the moon is d, the moon travels about 2 pi d in 27.3 days, or the days it takes for the moon to orbit the Earth completely. Based on this information, we can write an equation: a ratio of 2 pi d to 2r equals a ratio of 27.3 times 24 to 3.5. Solving this equation tells us that the distance to the moon is about 380,000 kilometers. When the rain pours and you are left without an umbrella, you'll be completely soaked. Therefore, knowing how to move without getting wet would be very useful. Interestingly enough, there's a map in Japan that tells people how to avoid getting wet. For example, it would show routes through underground passage or buildings with eaves, which would help people to avoid the rain. This application was possible because the surveying technique developed to be able to store more information on a map. The technology continues to develop that contains spatial information like 3D mapping is becoming more common. This also meant the role of surveying technicians also became more important. The purpose of surveying is to determine the size and direction of actual construction through accurate measurement of the site. Surveying selects base points on land and determines locations between buildings, which enables constructors to build large structures based on preset plans. Surveying technicians measure both things on the ground and any infrastructure underground to measure and draw 3D map. As the map integrates with IT, the application potential is enormous. Why is it important to create a standard? Standard time is based on the diurnal motion of the sun. This means the solar time can be different depending on the longitude of a location. A country can have different standard time depending on longitude, which is why for convenience, a country would select a region to be the standard time for the entire nation. Typically, an hour is added for every 15 masculine ordinal in longitude. Today, a country will select its own standard time to be used. However, selecting standard time was no easy process. On October 13, 1884, the International Meridian Conference held in Washington, D.C. chose Greenwich as the prime meridian. This means the global standard time was finally set. At first, other European countries refused to follow. In particular, the French were adamantly against it, as it didn't want to give up global standard to England. France argued that Paris should be the prime meridian. However, most European shipping companies were already using maps with Greenwich as the prime meridian. In the end, 22 countries of 25 countries agreed to select Greenwich as the prime meridian. French vetoed in this voting. French argued that if England gets to set the prime meridian, its metric system, meters, must be set as international standard. This was a trade of the prime meridian and the metric system. For France, if the French metric system was set as the international standard for volume and weight, England could have the prime meridian. However, the result was not what the French hoped. England refused to accept the metric system, even though they won the prime meridian. However, as EU member states decided to use the metric system as the standard measurement system in 2010, England had no choice but to give up its imperial unit system. However, the US still uses this system today. Although the prime meridian was selected, it was not accepted by everyone. A German map published in 1897 shows that Europe was divided into 3 regions. Western European Zone was where Royal Observatory of Greenwich was located, and the continent, including Germany and other countries, used Central European Zone. Moscow was denoted as Eastern European Zone. Today the international date line is longitude 180 masculine ordinal, but this is opposite from Greenwich, England. The date line, located between Alaska and Kamchatka of Russia, was purposely put on the Pacific Ocean and not on any land or island, to avoid any confusion. In 1835, Germany built its first train that connects between Nuremberg and Fürth, which is about 10 years after England. However, the pace of the industrialization was faster than any neighboring countries. Only 15 years later, in 1849, Germany was able to have one of the most advanced railroad systems in Europe. These railroads made it possible for Germany to reunite, led by Prussia. Thanks to the railroad system, Prussian military leaders were able to execute military plans more quickly and accurately than any of its neighbors. Although Prussia unified Germany, for the next 20 years, Germany had 10 different time zones. The time in southern Germany, such as Munich, was 7 minutes behind northern Berlin. In addition, Munich was 23 minutes ahead of Württemberg. Since there was no unifying standard, every region had different times. But everyone was against standardization because people believed that changing time would bring chaos to local people, who held regional festivals and events on their own time zones. Another opinion was that the sundial on church walls would become useless. The resistance from farmers, who relied mostly on nature's clock, was the fiercest. But one speech was able to persuade everyone. The speech was by General Helmuth von Moltke, who served as the first chief of the German General Staff. A month before his death, on March 16, 1891, he made a speech on the importance of train on the transport of military personnel. He also added the problems that can arise if the train time is not unified. Every German was touched by the speech of a war hero, who witnessed the strategic importance of the railroad in a victorious Battle of Königgrätz that defeated Austrian Empire, and the 3 battles that laid the foundation for the Prussian Empire. On April 1, 1893, Germany officially announced to follow the Central European Zone, and the entire country began to use single time zone. The importance of standardization in education can never be more emphasized. Education that focuses on the supplier, or the provider of education such as teachers, is no longer capable of producing a workforce that can sustain a country or a company. We must shift our focus to the demand side, where education focuses on the actual consumers of education, our children. This will be the only way for our children to be competitive in this new world where the boundaries between goods and services have collapsed. True consumer-centered education means each student will have individual teachers, with the right content and assessment. To this end, books should serve as a bridge between supply and demand rather than a medium that teaches information. For books to be a channel of communication between education suppliers and consumers, math textbooks should be written in natural language and follow international math education standards. Becoming the international math education standard means that math should be the study to uncover the secrets of nature, and studying math should be understood as the process of understanding nature. A proper textbook must contain information on how to understand nature, people and their society.